Hello everyone, and welcome to today's chem lesson. Today we are going to continue our discussion on naming ionic compounds by introducing the idea of polyatomic ions and then talking about how that changes our rules or adds to our rules for naming ionic compounds. First, let's define a polyatomic ion. This is the first time we're seeing them, and so let's look together. Polyatomic ions are listed on reference table E for us in the reference table, and what it is, right, if you look at any polyatomic ion, it is a group of atoms that have come together and bonded and collectively lost or gained electrons. For example, if we look here at sulfite, it's 1 sulfur and 3 oxygen atoms bonded together, and then after they have bonded together, they have gained 2 electrons. This is an interesting property for polyatomic ions. It gives them both covalent bonds within the polyatomic ion, and then allows them to make ionic bonds with another ion. And this means that they are almost always treated as a group. When we look at something like carbonate CO3, that CO3 is going to stay together, and it's going to take a lot to actually break up the carbon from those oxygens. Looking at reference table E, we get the formula, we get the charge, and we also get the name for each polyatomic ion. And the fact that they give us a name is actually pretty important, because when we look and we use a polyatomic ion and have something that contains a polyatomic ion and want to name it, it keeps the name that you see on reference table E. Last time we talked about table salt, sodium chloride, and we said that sodium, the first ion, the positive ion, keeps its name, where the second ion, the negative ion, gets its ending changed to "ide." That does not happen for a polyatomic ion. Lithium with NO3, which is nitrate, we can see that right here, is called lithium nitrate. We do not change the ending. We do not mess with the names of these polyatomic ions as they're given to us in the reference table. And this changes our crisscross method just a little bit. And when we introduce polyatomic ions into our compounds, it means we have to take a little bit of extra care when we go from formula to name, when we do that crisscross method. So let's take a look together at some examples and see how the crisscross method is going to change with the addition of polyatomic ions. Here we have the same steps that we saw last time, the same set of steps, the same color coding, but a set of compounds that contain polyatomic ions. And when we do these steps out, we're going to notice that there's 2 big changes. The first step, where we assign our ones, and the step where we check the periodic table, are going to have some adjustments made to them. For the first step, it's not just assigning ones, it is assigning ones and finding the polyatomic ion. Because if we just carried on with our crisscross method as we learned it, we would be given Fr2, C2O4, and have to crisscross this. And how do you crisscross 3 different things? You can't. There's no way for us to take one number and drag it across and then in any way that's fair. Right? We can't crisscross 3 different things. And so we know that there must be a polyatomic ion in here. So our first step when we identify our elements and assign our ones, we also need to find the polyatomic ions and capture them in these parentheses. We can find them just by looking at table E. We can look for Fr combined with C and see if that's on here, but if we take a quick scan, right, there's no Fr on here at all. So we're going to look for C2O4, which is right down here on the on table E for us to find. So we put our parentheses around it. Now we have 2 ions to crisscross. We've got our francium and our oxalate, which means we can move on to our second step, which stays exactly the same as it was last time. We're going to take our 2 from the francium and bring it up and over to the oxalate. We're going to take our 1 from the oxalate and bring it up and over to the francium, which is going to bring us to assigning our charge. We know our first ion is always positive, second is always negative. And then we're going to check the periodic table. And this is the other piece I starred here, the other piece that's a little bit different. When we check the periodic table now, we're also going to check table E. Because while we can find francium on the periodic table, we can't find a polyatomic ion, something that's made up of multiple elements, on the periodic table of elements. So when we go and we check, we're going to look here at table E, find our oxalate again. The -2 here matches what we see from our crisscross method, so that gets a nice check. And then we check francium by looking at the reference table, periodic table. Does francium have a +1? Yes, it does. And so we give it a check. And that brings us down to our name. First ion is going to keep its name. The second ion gets its name changed to "ide" normally, but here we have a polyatomic ion, and so it will keep the name that we saw for it on table E. Do we need a Roman numeral for this name? Let's double check. The only time we need a Roman numeral is if our positive ion has multiple options. Are there multiple options for francium? No, there are not. So we do not need a Roman numeral, and our name is done at francium oxalate. Let's take a look at our next one, right? Let's look at magnesium and this PO4 polyatomic ion. Our first step is going to be to assign our ones. And here we've got a lot done for us. The only one we are missing is right there. The magnesium has a number. The oxygen has a number. The polyatomic ion is already found and marked. Right? There's not one of them, there's 2 of them this time. So the only thing we need to do in step 1 here, assigning our ones, is put a 1 for our phosphorus. Then we're going to crisscross. We're going to take the 2 and the 3 and bring them up and over to their corresponding opposite ion. And we're going to assign charge. We know our first ion is always positive, and our second ion is always negative. Now we're up to checking the periodic table. So let's start with magnesium, right? Let's see. Mg is right up here. It has a positive 2, so it does match with what we wrote for it. Right, that +2 matches. We're also going to take note here, there's only one option. So we will not be needing a Roman numeral. Check. Wrong color. Let's try again. Check. Now, we're going to jump over to table E and take a look for our PO4. We're going to look, we're going to look, we're going to look, we're going to look. We're going to find it right here. PO4 has a charge of -3, so it matches what we put. And its name is phosphate, which we're going to note for our next step, which is naming. Both of these match the periodic table and table E. And so we move on and we say magnesium. No Roman numeral necessary because magnesium only has one option. And then right off of table E, phosphate, the name of the PO4 polyatomic ion. Not a lot of change from what we saw before. Let's look at our last example here. Here we have to assign some 1s and also find our polyatomic ion. Right, one of these things, one of these pairs, is a polyatomic ion. And so we will consult table E. Do we see anywhere on here something that matches a piece of what we have in our compound? Right here, we have CO3 together. And if we take a scan, we notice that there's no F's on this table at all. Fe, Fr, F, nothing. And so we know for certainty here that our CO3 is our polyatomic ion. So we're going to put it in parentheses and mark it with a 1. And then we're moving on. We've got Fe1 in parentheses CO3 1. We are going to crisscross, bringing the 1 from the carbonate up and over, the 1 from the iron up and over. We're going to assign our charges. We know our first ion is always positive, and our second ion is always negative. We are going to consult the table. Table E tells me that carbonate can only be a -2. And so carbonate does not match the table. The periodic table tells me that iron can only be a +2 or a +3. So it also does not match the table. So here we've got two elements, or an element and a polyatomic that do not match the table. Carbonate can only be -2. Iron has to choose between +2 or +3. When we get something like this in a situation where something doesn't match the table, we must adjust. We're going to need to double these charges or triple these charges or quadruple these charges, multiply them both by the same amount to make them match their table. Here, carbonate must be doubled in order to match its only option on the table. And if we double the carbonate, we must also double the iron. Now they both match their piece of the reference table, so we give them nice checks, and we move on to our name. Iron keeps its name, positive ion always keeps its name. Here we have a polyatomic as our second, so it's going to keep the name off of table E. And we do need a Roman numeral this time. Because iron can be +2 or +3, because it has multiple positive options here, we need the Roman numeral to tell us which version of iron we are using. Iron +2 means we're going to write a 2 here. The Roman numeral always matches the charge of the positive ion. Now, I do have some practice problems for us. Each of these practice problems has a polyatomic ion in it. Each one of these is going to need table E. And I'm going to give you about 1.5 minutes of on-air time to work on these. And again, please remember, if you need more time, pause the video. When we look at these compounds and get their correct names, it should look something like this. Each one of these compounds contains a polyatomic ion. And when they're not noted, right, where they're not already placed in parentheses for us, we have to do that ourselves. Most of the polyatomic ions on table E are negative, and so you will most often find them in the back of the compound. There are a few positives, right? Ammonium is one example of that, and it is totally possible to have a positive polyatomic bond to a negative polyatomic. Next time we're going to focus on going backwards and taking the name and getting the formula. How do we reverse engineer the steps of the crisscross method to go from name backwards to formula? But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.